Water skiing is simple. You put on these skis so you float, and then the boat pulls you across the water. Fun! Whoa. Maybe it's not so easy. Everybody knows you can't walk on water, right? I mean, that's obvious. You try to stand on water, you sink.
So how does a water skier do it? They seem to stay up on the water, no problem.
How does a water skier walk on water?
To help us figure it out, we've got Ronnie Barton. She's the world overall record holder, a 3-time Masters champion, and a 2-time U.S. Open champion. If anyone knows about staying up on the water, it's her.
Okay, Ronnie, what's the deal?
Staying up on skis is all about equilibrium.
Equilibrium, like balance? Is balance what keeps you up?
Well, you do need balance once you're up on your skis, but balance isn't what keeps you skiing. You need a balance of forces. That's equilibrium.
Forces, okay, so we need to know about forces.
Right.
Okay, guys, what's the first thing we need to know about force?
Well, force is a vector quantity.
Yeah, but what does that mean?
That it has both magnitude and direction.
How much and which way?
Okay.
In metric units, we use newtons to measure force. Like, if I had a quarter-pound burger, that'd be a 1 Newton burger. A lot of people think that kilograms measure force or weight, but that's not true. A kilo is a measure of mass. That's different. Like, if I had a burger with a mass of 1 kilo, that would be 2.2 pounds of force, or 9.8 newtons. That's a big burger.
You know the word components? Like a radio or a computer has lots of components? Well, all these pieces are components. And that's the totally cool thing about working with forces. We can break them down into their pieces. How much and which way? Okay, Ronnie, what's the next thing we need to know about forces?
The force components can be added up. If the sum of the forces equals 0, there's no acceleration. That's equilibrium.
Right, like sitting here, my weight is pushing down on the seat, but the seat is pushing back against me with an equal and opposite force. So if we added them up, the sum of the forces would be 0. There's no acceleration.
Right.
Now, acceleration isn't just going faster.
In physics, acceleration is defined as a change in velocity. Velocity is also a vector quantity.
So a change in velocity is a change in speed or direction. That's acceleration.
Right. If you're moving in the same direction or at a constant speed, there's no change, so there's no acceleration. It's only when you change your speed or change your direction, then there's acceleration.
Forces don't have to be applied in opposite directions to be in equilibrium. A whole bunch of forces can be acting on an object and it's still in a state of equilibrium. Tyler, you're not accelerating, right?
Right.
Well, that's because the sum of all your upward components must equal the downward force of your weight. And we know that because you're in equilibrium.
Cool.
Okay, now if the forces did not equal 0, then we would have acceleration. See? Acceleration. Tyler accelerated this way. Now, he's in a state of equilibrium. Because the sum of the upward and downward forces equals 0. So no acceleration. If we added up the two forces on this water ski, we would get a sum or a net force of 0. We know that's because there's no acceleration. It's not moving. But if I tilt it to one side, there's still the same amount of force down, gravity, and the same amount of force up, the sand, but they don't line up. They don't both pass through the object's center of mass, so they're out of balance. When forces are out of balance, there's an angular acceleration. The imbalance rotates the ski, spins it, and we call a force that rotates an object torque. Torque is a rotational force, and it's also a vector.
There are a lot of forces at work on a water skier, but in order to stay up, there has to be equilibrium. Okay, guys, now we know how forces work, but how are we going to figure out which forces are at work to keep Ronnie up?
When you want to figure out a problem involving force, use vectors.
Yeah, because force is a vector quantity.
These arrows we've been using, they're called force vectors, and they're what we use to figure out problems involving force. We use a Cartesian graph to map our vectors. The units of measurement we use are in force, like metric newtons. This way we can draw our vector arrows to scale, so that their size represents their magnitude, and the way they point is their direction. Because of the graph, we can say that they are either positive or negative. Forces can be mapped like this in 2 or 3 dimensions using I, J, and K axes. Putting them on a grid lets us see what's going on really easy. Okay, Ronnie, let's figure out which forces are working on you when you water ski.
Okay, well, the first one would come from the pull of the boat. That's conveyed through the rope.
Right. We'll put that force here. Okay, what's next?
I guess there would be gravity. It would be pulling my weight down.
Right. All right. There's gravity. Anything else?
There must be forces coming up through the water pushing against my ski.
Right. Okay, we'll call the force of the water pushing up against you the normal force of the water. On our grid, we can draw all our force vectors to scale, and then we can see if all our forces balance out. Look, there's nothing to balance out the tow force. That's going to create a lot of torque in this direction.
There's no force to cancel out the tow rope. You're going to rotate forward. That means free split!
And look, there's no up force to balance Ronnie's weight. Just a tiny bit of normal force. The friction and tow forces don't help keep her up at all. Ronnie, we just proved it's impossible for you to water ski.
That's because I don't ski like this.
What do you mean?
Well, my ski isn't flat in the water, and I don't stand straight up and down like this. When I ski, I actually lean back, and my ski is angled up in the water like this.
Well, that changes everything. With the ski at an angle, the water rushing against its surface is going to apply a force in the form of pressure. Now we'll call that the normal force of the water. Now let's take a look at what this does to our force problem. The direction of the normal force of the water is perpendicular to the ski. With Ronnie leaning back, the down force of her weight is out of line with the up force of the water. That creates a torque, right? That torque goes the opposite way and balances out the forward torque created by the tow rope. And look at the direction of the normal force. It has positive components on both the I and J axes. The vertical component is going to equal Ronnie's weight. The horizontal force combines with the reverse torque to equal out the tow rope force.
All our forces balance out. Equilibrium. Nothing accelerates and I stay right here on top of the water.
With just the components of the force, our problem would look like this. Okay, now we've shown how you stay up on the water when the boat's moving at a constant speed, but what happens if the boat accelerates?
Well, the boat is actually accelerating when I get up on my skis, and I compensate by just leaning a little bit further back.
Okay, well that makes sense. The boat's acceleration would mean a greater force on the tow rope in this direction. By leaning back, you increase the torque caused by your weight and the normal force, and also the normal force of the water has a greater horizontal component to balance out the increase in the tow rope force.
Right, and as the boat decelerates, I actually lessen the angle of my lean.
Wow, so your lean is a measure of acceleration.
I never thought about it like that, but yeah, I mean, that feels right.
Cool. Okay, guys, so what did we learn?
That force is a vector quantity. It has both magnitude and direction. And that when force is at its angle, we can break down both its horizontal and vertical components.
When all forces and torques are in balance, it's called equilibrium.
And even though there might be forces acting in all different directions,
The sum of those forces is zero when they're in equilibrium.
and when there's equilibrium, there's no acceleration.
And that's why the water skier stays up on the water, because of equilibrium.
And we use force vectors to figure it all out.
Okay. Good work.
Well, that's it. We'd like to thank Ronnie Barton, and our students, Kara, Tyler, Tina, for helping us out here today.